I'm going to talk about cadmium zinc telluride, mostly talk about for SPECT, and then also a little bit about CZT for PET. Okay. So just a reminder where we are, Stanford, that picture I just showed you down there. And actually, if you look at the British Columbia and California, um, you sort of have provinces, we have states, but you see British Columbia is just sort of a big version of California. It's really interesting that the shape is almost the same. So you're kind of our big brother. You engulf California, but like we have nice national parks. British Columbia has many nice national parks as well. So, but anyway, interesting picture comparison between California and British Columbia. And there you see Stanford Campus One view of the earliest, the oldest part of campus coming up Palm Drive. It's called Palm Drive, obviously, because it's got about a bunch of palm trees. It doesn't always look this nice and sunny. Right now, it's very gray, overcast, and rainy a bit. This is my laboratory within the molecular imaging program at Stanford. We have lots of different labs in the MIPS. I think last I counted, we have about 600 people in MIPS. So we're just a small part of MIPS, working on, we hope, big things. So molecular imaging program at Stanford, and our lab is called the Molecular Imaging Instrumentation Lab. And we have, physicists, biologists, bioengineers, material scientists, mechanical engineers, applied mathematicians, et cetera. So big, diverse group. Most of the time when we're actually trying to translate some of our work into, either human imaging or small animal imaging, we work with other outside collaborators because our lab is mainly sort of electrical engineering and physics and computational in nature. So just as kind of the breakdown, we have lots of projects. Most of the efforts actually more in computational areas, signal processing algorithms, image reconstruction, data corrections, a lot of the AI applications in imaging and medicine. We do also build things too. We build some labs. So if you come to our lab, you'll see various pieces of equipment built in various stages from very early benchtop detector measurements all the way through full systems that are built. And then once in a while, some of these tools make it into the clinic or in animal imaging, animal research. So we do try to bring everything and translate everything we can, but sometimes system doesn't work or things like that. But we do have a significant effort trying to bring things into being used so you can characterize molecular signatures of disease in living subjects. And then also once in a while, something that seems to be work really well and might even be a good product. So we'll interact with industry. We do have startups, but we also mainly interact with big industry to try to get them to use some of the things we developed. And students really like that impact where you can, in addition to publishing papers and presenting work, you can actually get some part of your code in a system that ships around the world. That's really a great interest of some students. Here's the outline of the talk. Of course, we're going to talk about CZT, so I want to back up and first just a quick review of scintillation detectors, and we're going to do sort of comparisons between the two. Um, and then we're going to focus most of the talk on CZT SPECT camera configurations and results, and then say a few words about CZT PET and then summary. So scintillation detectors. So here you see scintillation detectors. I won't spend too much time. I think some of you are experts at this, but basically you have a crystal. It's wrapped with a reflector, except for one side, which is coupled to some sort of photodetector. Is most of the SPECT systems in the world still use PMTs, so it's still a great photodetector. And then signals come out when there's electronics, and then you can do various things after that for pulse processing. So a gamma ray coming from the patient, for example, or any gamma ray from some source hits the crystal. That energy is converted into a scintillation light, which bounces around the crystal gets collected by the photodetector, and then that light signal is turned into electronic signal, which gets amplified. In the case of PMTs, it's in dinodes. And then you get this very robust pulse coming out where each photoelectron created was amplified, but you still take it through a preamplifier and an amplifier, and then you can have some sort of discrimination or pulse height analyzer electronics. If you do an imaging camera, there's a more advanced version of this. So then a camera design is going to be a bunch of basically making that scintillation detector position sensitive. Hal Enger kind of developed this concept many years ago. Basically, you couple a bank of PMTs to a monolithic sodium iodide crystal usually, and then you also have to have collimator as well. So the gamma ray photon comes through. I'm not showing you the collimator, but the collimator is a way to sort of determine the direction of the incoming photons. The photon hits the scintillation crystal, light spreads over PMTs. Nowadays you're digitizing the PMT signals, and then you're coming up with the most likely center of mass of that signal to determine the XY coordinate. And of course, in a SPECT scan, you have to do this millions of times to build up an image. And in terms of QC, you radiate the camera with a uniform radiation and look for any non-uniformities, and either PMTs have to replace or be tuned so that the flight image is fairly flat for a flat source of radiation. So that's a scintillation camera. A CZT is also a crystal, uh, also an inorganic crystal, but it's not going to be producing light. Instead, what you do is you put electrodes on the surface instead of reflectors, like we did with scintillation crystals. You have a cathode and an anode. And this crystal, depending on how much it costs and the material and the fabrication, it might be up to 7 millimeters now in SPECT. But here certainly 2 to 5 millimeters have been studied quite often. And so then a gamma ray photon enters the crystal, and just like with the scintillation crystal, it interacts via Compton scatter or photoelectric absorption, both of them yielding a fast ejected electron. That fast ejected electron traversing matter leaves a track of electron hole pairs. And in the case of a crystal, electron hole pairs, and it also did that in a scintillation, but all that energy was converted into light. In this case, we aren't converting light. We have a large electric field between the two electrodes, and that track of electron hole pairs, holes shown with plus sign and electrons shown with minus sign, they immediately feel the electric field, the strong electric field across the cathode and anode. It could be up to a kilovolt of energy, a kilovolt of a potential difference between the cathode and the anode, creating a strong electric field. The holes will drift one direction toward the cathode. The electrons will drift toward the anode. And as they drift, they induce a signal on their respective electrodes. And that signal is an indication of how much electrons or holes were created, and therefore the energy of the incoming photon. So we don't collect light, which is kind of we don't have a middleman of collecting and converting light into electrons. We directly collect charge from a CZT crystal. And the energy and spatial information is extracted from the amplitude and location of those pulses. So position-sensitive CZT detectors just operate the same way. It's just that you're going to pixelate the anode and or the cathode. In the current designs of CZT, both for SPECT and for even for photon counting CT that use CZT, they use a pixelated anode structure shown there, little squares where they deposit metal onto the CZT. Now that's a whole science itself, how they actually deposit a highly conductive material. It's usually multiple layers, and get it to be intimately in conductive contact with the CZT crystal. It's really hard to do. And so fortunately that's been solved, but it is difficult. And there's two different types of manufacturers. One that makes 2 centimeter crystals in terms of the width. And that's, for example, EV products. And then there's the companies that make very large crystals, 4 centimeters, and that's kind of more the Israeli companies. So you'd see Spectrum Dynamics and GE, those crystals coming from Israel being in those systems. And the crystals shown here are 5 millimeter thick, but you can make them slightly thicker so that they can be more efficient for energies above, let's say, 200, for example, for lutetium-177. Um, and then I show you here these two coins, the American dime and the American penny, but this is no way indicating the prices of these crystals. They're very expensive right now. The cost has gone way down, but I think per area they're still more expensive than a scintillation crystal and PMT, but the cost is going down as they improve their yield. And I show you also the detector's edge on because in our PET design, that's what we're doing in order to make 511 kV photons are highly penetrating of CZT. And so you need about 4 centimeters thick of CZT to have the same essential stopping power as a LSO, which is the crystal they commonly use in PET. So keep that in mind when we get to the end of the lecture. So the way again, in that picture, that cartoon I showed you, the way you would make this a position sensitive CZT detector is by pixelating the anodes. You could also use strips, cross strips design, which we'll talk about later. And then same process. You have the gamma ray coming in, creating a track of electron hole pairs, which the holes drift one direction, the electrons drift the other direction, and the electrons will induce a current in the anode pixel of choice, and that gives you the XY coordinate. And then typically you could also get Z information as well, but they don't usually use that in SPECT. So comparison between CZT and sodium iodide, maybe one of the reasons why they've moved to CZT is that all the way in the right corner, the average photoelectron signal created per MeV, right, at least in the front end of it, is for sodium iodide is only about 8,000, assuming a 20% quantum efficiency of the PMT. CZT doesn't have the middleman of light creation collection into a photodetector, so you get a robust signal right off the bat. So that electronic signal that fundamental electronic signal noise ratio is going to be higher in CZT. However, the PMT, the sodium iodide coupled with PMT has a gain mechanism which makes the signals quite robust and makes it easier on the electronics or to develop electronics. CZT, even though 200,000 sounds like a lot, it's not much compared to a signal coming out of an amplified PMT signal. And so you have to have special sensitive electronics to read out CZT. So advantage is it has more efficient direct conversion of gamma ray photons into electrical pulses, and therefore you can get superior energy resolution, which, as we know, helps us to position events, but also to reduce background scatter. You select your electropixels for positioning, so your intrinsic spatial resolution can be carefully designed, can easily be less than 1 millimeter. They typically use on the order of 3 millimeter in SPECT system designs, but you certainly can design a electron pattern that has much smaller pixels if you had enough photon counts, and that's what they do in photon counting CT when they do use CZT, as some companies and researchers have looked at. They use much smaller pixel pitch on the anode electrode because you can justify it. You have much higher photon flux. In SPECT, you don't, so they typically use something on the order of 3 millimeters. You have a higher count rate capability in principle because you're not spreading signal across a monolithic crystal. You have a very focused charge collection process, and small pixels and parallel readout electronics. So you in principle could have a higher count rate capability. For example, I don't know, first pass cardiac or something like that if you needed the higher count rate capability. Uh, Small detector heads facilitate novel system geometry. So we can't make a giant single monolithic crystal of CZT because of the way you make of CZT. You can't, it's not like the way sodium iodide is made with pressure and temperature. You can make a very large crystal, a monolithic crystal. You can't do that CZT. So you have to make a bunch of small crystal and mosaic them together to make a big panel, for example. Um, and then even with these small crystals, there's a certain yield. Not every single crystal has is free of impurities, so it does drive cost up. But they are exploiting the fact that we use small detector heads, or we should just call them modules in CCT in some of these new designs, as we'll see. And then the crystal's non-hygroscopic, which is an extra bonus. You can have it sitting in air when you're preparing the system, building the system. And here's what I mentioned before, the energy resolution. So we see things that in, for example, a cobalt 55 energy spectrum, we see peaks that we don't see with sodium iodide. So you can see that 136 kV peak as well as the 122, which is the nominal peak in cobalt 55. And so, sodium iodide is in the black, much broader energy spectrum, but still, 10% at full half max is not bad, but you can get a few percent with CZT at 122 kV. Drawbacks of CZT, as I mentioned, cost of high quality crystals are free of defects. So you have to have small area modules, and even then, there's going to be defects. Lack of signal amplification requires special low noise electronics, and you almost always have to have an integrated circuit, not true for PMTs. And then more complex detector packaging. And I want to emphasize this point. This actually caused one of our CZT projects to fail. We tried to do our own detector packaging. When I say packaging, taking your crystal, putting electrodes on it, coupling it to some sort of circuit. That's the packaging. Very difficult for CZT. You need really a company, a well-established company expert in that area to do that stuff. You try to do that at some hokey lab at Stanford, you're going to fail at least initially. Now here you see one example package here. It's a little module, and it's very important how this is made and coupled together, and all the electronics that go on and integrate with the crystal and the readout and the board and all that. So, and then you can imagine CZT SPECT camera configurations. If you take this module and you can make a mosaic of it and make a big head. Of course, the bigger the head is, the more expensive it is. But here you see a system built by a company called Chromac. Um, and that's kind of that is kind of the standard way to extrapolate from a scintillation camera to a CZT camera. However, you'll see some of the more advanced geometries don't use panels anymore. But there you go, a CZT detector panel head compared to a scintillation camera head. Okay, so one of the first panel detector designs here, for example, might look like what we just saw. So just take those panel, take two of them, put them inside of a um, gantry, put a couple of collimator to it, parallel hole collimator, for example. That's what you see here in the GE 870 CZT system, which we had for years. Here you see some other geometries besides the the lower left, the one I just showed you. You see the D-SPECT system, which is a cardiac system up in the upper left. The Veriton CT, the SPECT CT 360 or full ring SPECT system, and then the GE version of that. And so first we're going to talk about spectrum dynamics technology. And then we're going to talk about GE technology. We're not going to talk about Siemens technology because Siemens technology is it's actually more like for CZT SPECT is more like this geometry. It's a panel geometry. They also were using mainly cadmium telluride which is different than cadmium zinc telluride. It doesn't have zinc in there. So the band gap of the semiconductor cad telluride is a little bit smaller and they have to do things like cool it. But anyway, um, because it's not this kind of interesting ring geometry, we don't have time to talk about the Siemens version of their CZT camera. But so the Spectrum Dynamics was, to my knowledge, the first company that created a CZT-based spec system, and it's this one in the upper left, D-spect. We had this here at Stanford for years. It was meant to do it's cardiac dedicated system. So you can see the panels are kind of this curved panel where the patient will put their arm over it, and then it would be focusing on the heart. But it had something very unusual that the detector modules would swivel back and forth, and we're going to talk about that a little bit later. And then they expanded this system into a full ring system that could do cardiac, but also other things as well, brain, body, and that's called the Veriton, and it's a SPECT CT system with a full ring of detectors. So we're going to just kind of look at the insides a bit of how it works. So it's a 360-degree arrangement of detectors, and each detector head swivels. It can swivel back and forth, collecting photons. So if you imagine a typical SPECT system where we take a panel detector and rotate, you do that so you can get samples of the response lines all the way around the patient. And this is doing that as well. It's just kind of making use of a 360 geometry in that you have small detector heads. Now you could in principle do this with a um, scintillation camera head, except you couldn't use PMTs because they wouldn't allow you to swivel because they're long, kind of long. But you could use photodiodes or silicon photomultipliers, for example, and you could create a scintillation head that does this. But so it doesn't have to be CZT to have this geometry. But this was a very convenient geometry for cadmium zinc telluride modules. And so one of the things that does for you, remember that panel geometry, the first kind of concept you might think of to expand a CZT detector into a SPECT, you would create panels. And you can see that there's a lot of unused detector area essentially in a panel shape. Whereas if you are able to arrange these small detector heads, or let's say small detector modules in a ring, you're going to have a much more larger detector area used. And also part of the detector, all the detectors are close to the body as possible as well. And that in the right sort of column of this drawing and in the standard panel geometry, that's not true. So that's kind of, as you can imagine, it's going to improve resolution because the distance from the source to the collimator in general is better. It's going to improve sensitivity in principle if they can focus on certain areas, which we'll talk about a little bit later. And the detector is scanning all the time within the patient. So let's see if I can get this movie working there. Okay, so there you see all the sort of just a more complex version where you have all the detector heads sampling the space, uh, swiveling across the field of view. And then you take them out, of course, because you don't want to hit the patient. And then you rotate by one of the sort of the detector gap distances so that you're filling the full space. And this is just to make sure you have all the linear and angular sampling. So they have to keep track where these response lines are coming from into the detector as it swivels around, and then as the gantry goes into the second scanning position. The bore size is the minimum is 23 centimeters. Of course, you can make up to 80 centimeters to fit larger patients. The axial field of view is 32 centimeters, which I believe is 4 times 8 of those 4 centimeter modules, if I remember correctly, but we'll see that in a second. Your scan mode, you can do circular SPECT, you can do body contouring SPECT for better resolution and maybe even sensitivity and focusing SPECT for higher sensitivity. Let's see, did I? This is the next one here. Okay, and the detector material, as we know, is CZT, the tungsten collimator. So they do this. They make these collimators not the usual standard way. They actually deposit tungsten in layers, and they have square hole shape. The detection efficiency is in principle very high. They have body contouring and safety mechanisms so that the heads don't uh, touch the patient essentially, but they can get close to the patient. And so if you go back, I didn't get a chance to talk about this here. So you can see them taking apart that design. Um, so it's sort of long detector modules, um, 32 centimeter. So it's eight of these 4 centimeter crystals. So it's 32 centimeter axial field of view. And you see the collimator coupled to the detector array. And then here's what they call the focus acquisition, where if there's an organ of interest, such as the heart, that they want to focus on, they don't care so much about the background. They want to focus on the heart. They can do this. They find where the heart is, find where the most activity is, and then in their second orbit, they just focus on the heart. See, so it's not going through the full space now. It's just focusing on the heart and sampling it. And basically, what that's going to do is give you more SNR, effective sensitivity for the heart, for that focused organ. And you can do this for the brain. You can do this for other parts of the body as well. Now, they say improved sensitivity. I believe that. Um, then they say factor four improved resolution, and I assume that that's volumetric resolution. So um, the the collimator distance to it's not because of the collimator, because that's the same in whether you do a full scan or a focused scan. I know that they do resolution recovery in the reconstruction. It might be something to do with that, but factor four improved, let's say, volumetric resolution. I'm not sure exactly how they claim that, but it's clearly an effective sensitivity for the heart. You're collecting more events from the heart in a given time. That makes sense. So scan modes, whole body scan mode, brain scan mode, cardiac scan mode. Um, You see some images from the body, brain, and cardiac. Very nice image, almost like pet looking image quality for the cardiac. So GE has its own version of this. And when you're looking at these slides, you're going to think, well, gosh, that's almost very similar to the spectrodynamic system. They have some differences in software, some difference in mechanical, but basic idea seems simple. And you're right. And I think there was a big lawsuit. So I don't want to go into that too much. Um, I have friends in both companies. I think that they have different customers, certainly different service, different ideas and on the different reconstruction. But the basic there was a dispute about the basic design, as you might imagine. But don't shoot the messenger. So again, the same reason instead of using unwasted detector area in the panel design, we have a design that looks with individual modules that swivel. Here you see this gentleman from GE. He's in the room with a face mask on. I'm not sure why, but anyway, he you can see how this is actually swiveling. I thought this was interesting. So it can always swivel all the way across, and then they've got I think 12 detectors in that 360-degree pattern. And here you see an actual patient being scanned, which I thought was interesting. Can you see the contour, you know, how does the contouring there? And the crystal is in the GE design is 7.25 millimeter thick, which they claim is very efficient for the 206 keV line of lutetium 177. So they're really claiming this to be a theranostics camera. And you can see how these detectors are sampling as we collect the data from the patient. So it's quite a complex thing. And we actually have the GE system, um, this thing here. Let's see. It's called Star Guide, but they call it digital focus detectors. So we have this, and when I first got there, I said, "Oh, within a year, these all this mechanical swiveling, it's gonna break down because the more mechanical parts typically in a spec system that you have, the more it breaks." But no, it really they not the when things go down, it's not the anything mechanically, believe it or not. So at least right now, we've had it for a few years, but I'll let you know in a couple of years. Here's a more sort of drawing of this again, and some information about the collimator. The collimator is also a tungsten collimator. It's about 2 centimeters thick. The septa is 200 microns, 1.025 holes, square holes, and you can see the attenuation of the holes of the photons in the collimator holes, depending on which angle it comes in. And there you see some lutetium SPECT CT images after the patient had went through a few courses of theranostic therapy. There you see the module in the upper left, 4 centimeters with high yield. There you see the energy spectrum, technetium 99. This is just showing you the different sort of absorption efficiencies of the different isotope photons emitted from different isotopes for this 7.25 millimeter thick crystal. But you can also get down to even a 5 millimeter thick crystal. I think you have a choice to buy different thicknesses. But if you're going for lutetium 177 SPECT imaging, then you want to use the 7 millimeter crystal. Here you see some comparison I thought was interesting between the Star Guide for 5 minutes, for 10 minutes, the panel CZT detector, and then their standard Discovery NM670. You can see the different image quality in the transaxial, coronal, and sagittal images. The best being in the Star Guide, of course, in terms of contrast to noise ratio for the image quality phantom. And here you see some typical image quality that you might get from a theranostic study with the Star Guide. And on the left is a MIBG image, SPECT image. The center is an FDG image. And then the right is a PET gallium-68 dotate. So this is probably neuroendocrine tumor patient dotate looking at somatostatin receptor overexpression, as is a MIBG. But if you look at the left and the right image, you might claim that that SPECT image is of comparable quality to the PET image. Maybe a little bit lower signal-noise ratio, but that's SPECT. So it's because of that swiveling detector design. And I guess in this case, they may have been focusing on this area in the head and neck where the neuroendocrine tumor is. So last couple minutes, I want to talk about CZT PET. So we had a NIH project for several years to develop a CZT PET system. It was a small animal PET system. And there you see the system there. That it was using CZT detector crystals ranged edge on, which I referred to earlier, so that the incoming photons see a minimum of 4 centimeter thick CZT, which is equivalent to 2 centimeter thick LSO. The photo fraction is a little bit lower in CZT than LSO, so you have maybe a bit more Compton scatter, intercrystal Compton scatter, but if you have good energy and spatial resolution, you can still come up with an accurate estimate of the first um, interaction in that 4 centimeter thick crystal, so that you can get pretty good image quality. We have several papers published, and then Shiva Abazadeh at UC Santa Cruz. She was a postdoc in my lab. She took this design and is building a head and neck camera, PET camera, and hopefully we can get that translated into the clinic for high resolution head and neck imaging using PET. Now, CZT is really great for some reasons, for various reasons. For example, energy resolution. As I said, energy resolution is used for better determination of that first interaction. Energy resolution also helps to reject scatter. Spatial resolution, of course, is selectable by the pitch of your electrodes. In our case, we're using a cross strip CZT, which I'll show you a picture of it, where the pixel pitch in the anode is 1 millimeter, so we can get really high resolution. So that would be an advantage of CZT. One disadvantage of CZT is that it doesn't get fast timings because you're drifting charge instead of collecting light. And the variance in the charge drift, you just can't get your couple hundred picosecond time resolution with CZT. If you're lucky, you can get a couple nanoseconds. So it's not going to be a time of flight system, but there are some other ways of boosting signal noise ratio with CZT that might somewhat offset not having good time resolution. Here you see our cross strip detector design depicted in the lower left, where you have electrodes anode. The anode is now not square pixels, it's a bunch of strips deposited onto the CZT. And again, we did this. We figured out how to do this. We worked with a company, of course, but we kind of designed this ourselves, and we put these steering electrodes between the anodes so that electric field lines don't terminate in between the anodes. So the steering electrodes kind of steer the electric field lines toward the anode so that as the electrons are drifting, they can collect the signal, the full signal. And then the holes are going the other direction, and we have a coarser cathode strip arrangement on the back, only 8 cathodes. So the intrinsic resolution is sort of, in principle, 1 millimeter by 5 millimeter, but then we can get sub-pixel, cathode strip resolution. So we can get it's probably around the order of 2 millimeter cathode resolution, so sort of 1 by 2. And then the third coordinate, which isn't necessarily important for SPECT, but definitely is for PET, because we're arranging these detector crystals edge on with respect to incoming photons. You need to have that third coordinate, which we would call, let's say, the Z coordinate, and that's the direction in between the cathode and anode. And you can get that a number of different ways. One of them is the ratio of the cathode to anode signals for a given event, or you can look at the time of arrival onto the cathode of the whole signal to determine that depth, and they both work pretty well. So you can get and that you can get sub-millimeter spatial resolution in principle. So you can get a pretty high intrinsic resolution detector system without having to cut crystals and put in reflectors and couple in photodetectors, but right now at a little bit higher cost. Here you see our arrangement of actual crystals, the 4 by 4 centimeter by 5 millimeter thick crystals, which we put back to back to another one. So it's kind of a dual module. Oops. There you see the dual module looking from the edge. And again, we arrange these detector edge on with the photons coming, let's say in this case, from the left, so that they see 4 centimeter thick of CZT. And you can calculate, of course, how many crystals you need to cover a certain area. And just to give you an idea, right now, each one of these crystals, I want to say, in the market at high volume is probably about $500 if you're looking up to buy a Christmas present for somebody that you like. But that's at high volume, and those companies usually won't sell it to you, so you have to find another one-off company. But here you see really good energy resolution. You can't get this with LSO. I bet you can get this with CZT. So I showed you that four panel design. We were able to build two panels, and we started building the other panels. And the other panels had a bunch of detectors that the packaging wasn't good. So we kind of, I want to say it was a half successful project, but depending on how you look at it, it could be a half failed project, just because the packaging was so different, was so difficult, I should say. But you can see the CZT detectors are ranged edge on. We had to develop all our electronics, the integrated circuits, readout, and there was going to be four of these panels. And here you see imaging, this case a source, but we also image a phantom. But the nice thing about this panel geometry is the aperture can change. You can slide these detector heads, and you can image a mouse or you can image a rat with very high efficiency. And then we were hoping to do something with humans too. And Shiva took this design. She worked with a company that's well established with CZT packaging, so she didn't have the same problems. She's gotten a lot further along and has now delivered a dual panel head neck camera on this system. So you can look at some of her recent papers. I think she's got another one coming out. Let's see. So in summary, we've reviewed CZT and scintillation detectors. We talked about the principle of operation. Design and performance are quite different between scintillation cameras and CZT-based cameras. The compact CZT modules enables this novel swiveling detector ring configuration that both Spectrum and Dynamics and GE have exploited to yield very high SPECT imaging sensitivity and really probably the best SPECT images you can see from any human SPECT system are from these systems, in my opinion. It's ideal for both organ-specific or body applications, and they're really focusing, of course, on theranostics because of the big um, role that SPECT is playing in theranostics these days. There's a high cost and mechanical complexity of these ring designs. So they're quite different and require a lot of learning about the system compared to a standard scintillation camera that we know and love. And then CZT-based PET system designs are under study. They won't be time of flight, but they'll be high resolution and especially high energy resolution with some unique geometries that can also have some advanced capabilities. So I will take questions.
Thank you. Thank you very much. Yeah, that was great. Thank you very much. Great. I've heard sometimes that this is fantastic. I've heard that these systems were not, at least at some point, not necessarily optimized for high energy imaging. There were concerns about like the tissue, tissue imaging, things like that. So
Yeah, that's right. So they no, they are looking at trying to increase the thickness of CZT, but I explained to you the difficulties of CZT getting high yield thick crystals free of impurities. So, what happens in these crystals is as if there's impurities present, they basically capture the both well in principle the electron hole signals. So they diminish it, they attenuate them, and the bigger the crystal, the more higher the chance that is. And so the cost won't go up linearly. It will go up quite exponentially if you try to make it thicker for some of these higher energy photons. So it is a problem. They're aware of it. What energies, photons were you thinking about?
But I mean, no, it's just a general for lutetium, basically moving beyond, technetium. When you look at theranostics, I think that's been the questions. I mean, just but and other ones in alpha imaging, for example,
Yeah, yeah.
um, with actinium now sort of becoming
Yeah,
more.
definitely. It's not definitely actinium. That's that photon's gonna go through this
Yeah,
quite a bit, so it's not efficient for that. And
yeah,
they're aware of this problem. It's just it's a limitation of CZT. So and again, it's not just as simple as oh well, let's make a 15 millimeter thick crystal because there's lots of engineering problems with that again, and not to mention the detector yield. So the cost would go way up to be able to get high quality detectors that are thick enough to have a 90% efficiency for stopping, higher energy photons.